Welcome back to the quantum optics series. In today's lecture, we shift our focus to the detection of electromagnetic fields, a crucial aspect of quantum optics. Here's what we will cover today: the semi-classical theory of photodetection, explaining how light interacts with detectors, first and second order correlation functions, which help us quantify the statistical properties of light, the concept of the average number of photocounts, offering insights into light intensity and its fluctuations. This lecture is foundational for understanding the experimental side of quantum optics and prepares us for exploring quantum theories of photodetection in future sessions. So let's get started. So the question is that how do we find an unknown state of the electromagnetic field, or how can we determine the state of the given quantum system? These kind of questions are related to the problems in quantum optics that involves the detector and the detection of the electromagnetic field, and indirectly the interaction of the field with the photodetector or any kind of detector apparatus. So in reality and in the laboratory, there are two kinds of detection techniques that we could use to determine the statistical properties of the given field. And the first one is the photodetection. And it usually involves the direct measurement or detection of the given field, and the field ionizes the material in the given detector, and this gives rise to the photoelectrons. And the fluctuations of the photoelectrons is the directly dependent upon the field properties, and we could get insight of some properties of the given field. But it has some disadvantage that in the process of detection, the field gets destroyed, and we cannot know about the fluctuation of amplitude, for example. So, in order to get the insights about the amplitude and its fluctuations, we usually use another phase-dependent techniques like homodyne or heterodyne detection. So the semi-classical theory of photodetection assumes that the given field, that is the electromagnetic field, is a classical field and it has wave behavior. On the other hand, it is also assumes that the given detector and its material is quantized and follows the rules and principles of quantum mechanics. So that's why it is called semi-classical theory, because it has some properties of classical theory and also assumes some principles of quantum mechanics for its formulation and its working. So consider we have a detector and it is situated at the position R, and we could define its position with a vector R, and the probability of photodetector is directly proportional to the intensity, and we are taking the average intensity of the ensemble. So the probability of photodetection at the time interval delta t is given in equation 1, and eta here is the efficiency of the photodetector. So we could also define the intensity of the given field in terms of its amplitude, and it is written in equation 2. And it directly characterizes the first order correlation function. So the first order correlation function define the temporal evolution of the field at different times. And when the field is constant, as usual in the classical case, the correlation function has value 1. But for some quantum states like squeeze states and photon number state, the correlation function has different values other than the 1. So it gives some key insights into quantum behavior of light. But for that purpose, we have to assume the quantum operators instead of the field amplitude. So we will talk about it later. So we could also define the probability of photodetector in photodetection in equation 3 in terms of first order correlation function. So first order correlation functions could be measured experimentally by taking the average of the intensity that we measure in photodetector detection process. So consider we have now two detectors instead of one, and their positions are R1 and R2, and their probability of detecting the incoming field and registering the photo counts is given in equation 5 and 6. And the eta 1 and eta 2 here are the efficiencies of the respective detectors. So if the detection process is independent of each other, as we could say the fields at different position are not correlated to each other, the joint probability of photo detection is given in equation 7. And if they are correlated, the detection process is correlated with each other, the joint probability of photo detection is given in equation 8. And we could see that if the process is correlated with each other, then the field must be correlated with each other. Then the product of the averages must not be equal to the product of the intensity and their averages. So we could define the second order correlation function as it gives us the temporal and spatial evolution of the field and the dependence of the field with each other at different position and at different interval of time. So in quantum states of light, it gives some properties of some key insights about the properties like key anti-bunching or bunching of photons, but we will talk about it later. So uh, for classical light, it has usually the value of 1. So we could write the joint probability of the photo detection uh, of two different detectors at two different position and measuring measuring the field at different interval of time in equation 10. So we saw that the probability of photodetector or single photodetection is proportional to the intensity and its efficiency. So uh, we could write the average photo counts in terms of the efficiency and the average intensity over the whole ensemble. So from experimental and observed data, we have come to know that the photo detection, that the photo counts detect or follow the Poisson distribution. So this means that the photo detection is a random process, as we could say that the photons in the light follows a Poisson distribution, and we cannot predict the uh, number of photons at a given instant of time. So we can prove that the average number of photo counts follow this kind of distribution by using the usual uh, definition of the averages, as it is the product of the probability distribution and the photo counts, number of photo counts. And we could make use of some mathematical identities here. So simplifying the process by taking the eta I part out of the sum, and simplifying the factorial that is in denominator by canceling out some terms with n at the uh, upper part of the fraction. So we came up with this kind of equation at the last line. So changing the variable and changing the limit of the sum, we can come up with that kind of equation. So this is just the exponential, the definition of the expansion of the exponential, and simplifying the remaining expression, mathematical expression, we get the result that is directly proportional to the intensity and efficiency of the photodetector. So we have proved that the photodetection phenomena follows the Poisson distribution. So if the intensity fluctuates at time, so we could make use of this function, that is the u of t and capital T, and when the intensity remains same, the it ends up with the usual intensity, that is the function of time only. So in that case, we could define the probability distribution function in equation 13, and the time dependence of the intensity and its fluctuation is characterized by equation that is given below it. So that is all for today. So let's recap what we have covered in today's session. We discussed the semi-classical theory of photodetection, laying the groundwork for understanding how light interacts with detectors. We introduced the first and second order correlation functions, which are essential tools for analyzing the statistical properties of light. We explored the average number of photocounts, providing insights into light intensity and its fluctuations during detection. These concepts are critical for connecting the theoretical and experimental aspects of quantum optics. In the next lecture, we will take this discussion further into the quantum theory of photon detection. Thank you for watching. Don't forget to like, share, and subscribe for more engaging lectures on quantum science. See you next time.